Well, hello everybody. Interesting times we live in, so we'll just have to do the best we can. And I guess we're engineers, so we'll have to solve the problems as they come up. So this is going to be my first attempt at doing a class online and giving it to you. If all else goes well, we'll have some Zoom sessions later on for questions and answers and stuff like that. But for right now, let's just continue on. So you've already got your results from the first exam. Please go ahead and do the survey that I sent you earlier. And I'll try to figure out a way to review that with you sometime later in the week and post that. So today we're going to start a new topic. This is the second half of the course. So we're going to start talking about displacements today. So I'm going to switch over and share my screen, and you'll get to see my slides, hopefully. There they are. So let's begin. So what are structural displacements? That's the big question. And we're going to talk about deflections today. The answer is that really what we're looking at is the movement of the structure and its components. And in our case, it's going to be beams, trusses, and we're going to look at that from the original displacement. So that's what we're going to call a deflection or a displacement. And of course, as a designer, you're going to be really interested in this kind of stuff. Displacements usually also relate to strains, and that can be limited by materials. Can also cause stresses, which can cause issues. And we'll find out too that one of the big design criteria that you'll have to worry about is not only stresses, strains, or the material is going to behave properly, but also is the structure going to deform within limits. So a maximum displacement criteria that's usually used in structures are stated mathematically by either the live loads or the dead loads. And you can see they're a function of, oops, I messed that up. Let me go back. They're a function of, oops, that's not very good drawing, but you get the idea. It's the length of the beam over some limit, or the for live loads and for dead loads. And the interesting thing here is that these limits are fairly small. For example, if you're in a very tall structure, say, the Willis Tower in Chicago, I've mentioned that a few times, and you're at the 110th floor, that structure could move many, 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 many feet and still not have a problem with stress or strain or any of those kind of things that would cause material failure. However, you would be very, very uncomfortable. So these are limits really on user kind of limits. So if you look at this, L maybe 10 feet tall, that would be 120 inches, 120 inches divided. You're talking about half an inch per floor times 100 floors. You can do the math. You can see there's a pretty small amount of movement that's required under those. So displacements are quite interesting, a little more challenging to compute, but very, very important to design. So we're going to talk about now how to do these things. Let me switch back my pen here in case I need it later. And we're going to talk about two basic methods. One's called a geometric method, which is based upon strain and the material behaving elastically. And then there'll be an energy approach, which is again based upon computing the energy done by external forces, loads, wind loads blowing on the beam, on the structure, live loads, dead loads, snow loads, all those things pushing the structure around, forces going through displacements. That's work. So that's external work. And then we'll conserve that energy by assuming the structure is going to store that energy internally in terms of like a strain. So really your structure is really just big springs as a simple analogy. And those springs will compress or elongate and store that energy. So before we do that, let's talk about to kind of anticipate or have some insight into displacement. So that ability to look at a structure and kind of see how it will deflect is pretty important. And of course, these can come from many different sources besides just the loads we've talked about. Temperature can cause displacements, construction error, settlements. Settlement's a big problem with foundations, especially differential settling. One side of your structure displaces more than another, and you induce some additional stresses and strains. So again, it's important to include these deflections into our design procedure. Secondary structures like wall, especially brittle materials like concretes or plasters, they will crack when they have differential settling. You might see that in a lot of older homes, especially around door frames and windows. You'll see cracking in the corners, and that indicates that basically each side of the door is settling in a different rate than the other. So we're going to talk exclusively in our course, since it's an intro course, about linear elastic structures. And you might recall that linear elastic means linear, that it follows a linear curve, which would be described by the modular elasticity, E, and elastic in that it will return. So whatever when you deform it and you unload it, it will return to its original position. If it doesn't, then that's plastic behavior, and that's beyond the scope of our course this time. So deflections are mostly caused by internal loadings. And in our case, we spent some time this semester already talking about axial force, shear force, and bending moment. And we'll find that axial force, shear force, and bending moment are the primary drivers of deflections in our structures. So before we can talk about deflection, we usually talk about slope and displacement. It's probably a good idea to see how those things will behave. So typically we use this notation. You can see here the theta is a typical notation for rotation or slope, and that's going to be the slope of the deflected curve. So if you can write an equation for slope of the deflected curve and take the derivative, then you would have the slope, theta. And then there's a lot of different symbols used for displacement. I'm using this one here, the delta. The book uses a lowercase v. I've seen y. I've seen a variety of different lowercase delta. I've seen a lot of different ones. But the most important things are just all trying to describe the movement of the structure. So here's a beam, a simple supported beam. You'll notice a pin on the left, a roller on the right. And now you apply some load to it. Well, right away, you know that here at the pin and over here at the roller, that the structure is not going to move vertically at all. Oops, wrong way. Sorry about that. So as it deflects, you can see there is no rotation at the supports, which we know that before we start, but there will be some displacement throughout the structure, as you can see here, delta. I just indicated a point near in the middle, but really you can see that delta is continuous across the entire length of the curve. And you'll also notice, if I know that deflected shape, that the slope will be, we can know that. So in this case, here is the slope on the left side at the pin, which I call theta 1, and then there's a different slope over on the right side at the pin, or the roller, theta 2. You'll notice that on the left side, the slope is negative, gets increasingly smaller till about right here, where the slope is 0, and then it proceeds up positive. So 0 slope indicates that the curve has gone flat, and we all know that horizontal or flat parts of our curve indicate a maximum or a minimum. In this case, it would be a maximum or minimum slope. Displacement. So again, pins and rollers, we know by definition have no displacement. This is displacement vertically, not horizontally. Now another typical support that we have is fixed connection. So in that case, we know that if we apply a load here at the end of the cantilever, we know this point's going to definitely move down. And then we can see that the deflected shape would look something like this, with a deflection here at the end, a maximum displacement. And you'll notice over on the left side at the cantilever that I have not only no slope, but what's unique about a fixed connection is also there is no displacement, no rotation. So again, pins and rollers will have no displacement, some slope, something that we'll have to compute. A fixed connection will have no slope, no displacement, but everywhere else in the beam will have slope and displacement. So those will be in conditions that we'll use later on when we do some problems. So let's consider rotation and displacement of connections in a frame. It's a little more complicated, but if you assume that the frame, this is where this section here, the two frame elements are fixed connected. So if whatever the load is, if you'll notice that the beam at the top rotates through an angle theta, then its mate or its connected mate through that rigid angle will also rotate initially through the same angle. So that edge, that fixed connection joint is maintained. So if it starts off, say 90 degrees, it's going to stay 90 degrees. Now, on the other hand, if you have what's called a pin connected joint, then you could have some kind of rotation through the first part, say the beam, which is theta 1, and when it rotates through, it will not rotate through the same angle, say theta 2. Those are not equal. So you'll notice now that that connection, that 90 degrees did not maintain. So this is kind of a partially restrained connection. We won't have too many of those in our course, as you might remember, but you might all remember from our SAP 2000 work that there is a place where you can put in partial rigidity in frames connections, and that's where you could do something like that. So let's see how all these put together in a beam. So here's a beam. You'll see it's fixed connected on the left and a roller there on the right, and I push down here on the right. So what's our intuition tell us about this? Well, let's see what we have. First, we know that we have at the connector, we have no rotation, theta 0, because it's fixed. And we also know there's no displacement there. So that means starting on the left-hand side, we have no displacement, and also we know the slope is 0. And then it proceeds over to our roller connection. The only thing we know about the roller is that the displacement is 0. So what do you think will be the beam displacement? So I'll give you a second or two to think about that. So let's see what we do know. I'm going to kind of change my highlighter here to give me a little bit heavier notation. So I know here at this point that I am definitely going to move down. That part of the beam has to go down. And then, of course, for it to be down here and to rotate up to 0 here, I've got to have something like this. So that part seems right. Well, we're not going to have any kind of super bending or a hinge here, so this is going to continue up. I also know that I'm going to start out 0 here, and I'm going to come out pretty flat. So if you just try to then connect those two, you can see you'll get some kind of general displacement that looks like that. And then I penciled in a little nicer for you to see. Okay, so let's move that one around. Let's use the same kind of structure with the same conditions, except that you can see I've moved the load over here to the middle. So I know when I push down here, more than likely this beam is going to want to go down. But the conditions are the same. No slope, no displacement, the fixed connection, no slope. No displacement at the roller. So how's that going to behave? Well, again, we're going to come out pretty flat here, but I've got to get down here, so I'm going to have to bend down and then go back through 0, and then I'll have to seesaw up. So in that case, the deflected shape may look something like that. Whoops, that was a mistake. Sorry about that. So let's look at it again. Now here's the same kind of exercise we just did, but you'll notice here on the left-hand side now that it's not fixed connection, it is a pin. So under those conditions, I'm going to push down the right-hand side over here. You can see that I'm going to have no displacement at the pin and no displacement at the roller. So how's that going to deflect? Well, again, this has got to move down. Got to be 0 here. So again, we're going to seesaw through here. And I got to connect here. So this is going to be kind of a curve. So it looks something like that. And again, there's my dotted line, kind of make it a little more formal looking. Okay, now I have the same scenario we had before, except I'm going to put the load in the middle span. Same end conditions as we know, no displacement at the pin, no displacement at the roller. So how's this going to deflect? Well, again, I'm going to go down here. I'm going to push the structure down. So again, starting at 0, I have to go here, and then back, and then have to seesaw up. So I'm going to get a shape that looks something like that. Now, it's a little more complicated with frames, as you might expect. So I'm going to kind of walk you through this to see what you can see. So here's a frame. This is a fixed connection, fixed here, roller here. So I'm going to push down on this structure. So I know I'm probably going to have to come down a little bit. So I'm going to get some kind of bending in this shape. But these are fixed, so this is going to have to kind of stay right angle, so the way they were before. And then this is going to bend out and have to come back in here straight up and down, because I know this is going to come out 0 slope here. And this one's free to rotate and do whatever it wants. So if you kind of connect the dots, or in this case, the line segments on this one, you'll get something that looks similar to that. So let's try this again. Same frame, different force. So now I'm pushing the force over on the left, which you can see probably looks kind of like a wind load. So I know my structures kind of have to move to the right. Well, I'm going to have to still come out here straight, and pushing it to the right is going to come like that. The whole structure is going to the right, so this one's going to kind of have to go like that. This guy's 9 degrees, this guy's 9 degrees. You can see it's going to have like a little twist to make it fit. And you might get something that looks like that. And just to show you I'm not making this up, I ran these in SAP 2000. You can see what the deflected shapes look like for the same frames that we just talked about. So this is something you'll develop as we go along. You'll get some kind of insight, some intuition on how you think the beams will deflect, and that will help you in your calculations. We'll have a sign convention, you know, positive will be up, negative will be down, say on a beam. And if you think this deflection will be down, you should get a negative. If you don't, then maybe something's wrong. You want to check your numbers, check your calculation. So again, if you have a difficult time drawing these things, a lot of people do, it's not a big deal, but you can also use the moment diagram to help you do this. So for example, if we had a simple supported beam, we've looked at several of these throughout the semester, and under this particular loading, if I gave you some time, I'm pretty sure after the first exam results, I think you all could do this moment diagram. If it looked like this, so there's a point of importance, so you get a moment diagram. And you'll notice the whole moment diagram is positive. You might remember that positive bending moment means like you're smiling, it's concave up. So the deflected shape should look like a big smile, concave up. So positive bending moments are going to have this concave upward behavior. So again, if you see the beam, draw the moment diagram, it'll give you an idea of what you think the displacement should be. You're making calculations on this beam and you say, hey, the displacement here is positive. Well, we know that's not true. Positive is up. So what about this beam? What sets this beam apart? Well, it's kind of an odd situation, but I did this as an example to show you that, again, given some time, you can draw the moment diagram. And you'll see there's a section that has a positive moment and a section that has a negative moment. So if I'm going to try to draw this shape, you can say, hey, well, over this first part, it needs to bend something like that. And over this last part, that's negative, it should be a frown. So look at that. You've almost kind of visualized what the displaced shape should look like. And there you go. So again, positive moments are going to be concave up shape. Negative moments are going to be concave down. All right, so before we get on to our first solution process, I need to take some time and derive elastic beam theory for you. And I think what I'll do right now is I'll just take a break and we'll stop here, and I'll just call the first one video 1 or part 1, and then I'll call this elastic beam theory part 2. So I should come back on here. Let's see if I can make this work. I need to stop sharing my screen, and then I'm back to you. So this will be the end of this section, kind of the intro to displacements. And then we'll pick up the next video. We'll start right where I left off, and we'll do the elastic beam theory. All right, see you in a minute.